So right now, the program basically is counting. It's counting a number from 0 up to the 8-bit, the maximum number from 0 to that one, if you push the button. But now the button is not working as a switch. It's just another sources external to activate the interrupt program. Because you know that 3 interrupt sources. The first one is RB0, internal, external. The second one is RB4 to RB7, and the last one is timer 0 overflow. So the first one we are playing around is this one, RB0. You have to use a switch. When you push the switch, the interrupt function will execute, and that interrupt function is basically counting a number. So the one that you see over here is likely only LED in binary. So what we are going to do now is, I'm giving you this component. This component is L274LS47. That is a driver to count from binary and put it to the 7-segment display. So right now, you have the output from port C, right? So you can connect all the first 4 to the 74LS47 here. This is the first one. This is the second one. This is the fourth one. This is for the second wire. Third. And fourth. This is a 7-segment common anode. Common anode means it's sharing the same anode. Power over here. So you have to find this one. The name of the component you can try to find is over here. This one, which is they call it 74LS47. And another one is 7-segment.com-anode. So that is a particular component. Once you connect all of them, you run again the interrupt function. That's a new component which you can see on the board also. On the board there are 2 components with the driver. 74LS47. Once you finish, you run back the program and look at the results. Okay, ready? Alright. So in this practice simulation, a lot of people confused over this one. But right, it's very simple. This is basically a counter by using a binary numbers for 8-bit only for port C. So no matter what, if you have 1, it will be here, 2 will be here, 3, this one on, 2, 4, 5, 6 and so on. So it's a bit confusing because you don't really familiar with the binary, you just understand like that. But now we have another driver, they call it 74LS47. This driver is to change directly the input, 4 bits input to 7 segment display. So this counter 7 segment, you only can count from 0 up to 9 only. Okay, 0 to 9. So that's why right now you can see that the difference on the program. So go back for this one. So for the interrupt, now, the difference from the switch just now you can compare side by side. Where the switch is basically the programming will be inside main loop. Whereas in this interrupt function, also use RB0 as your external input. The thing is, for the interrupt, it will have this void interrupt function. No matter what, for interrupt, it must have this void interrupt function. Okay? Now look at your main program here. My main program now, I put try C all 0. 0 means all output for all this port C. Port C now, I put all 0. Go for 0 level. Now you look at try B. Try B, only one as input, which is RB0. You know that interrupt must be using this pin. Must use this pin as external. Now port B is, you can remove this one, it doesn't matter, port B is equal to 0. The next important register need to be changed. They call it incon, which is an interrupt control register. Once you declare this one, you are trying to play around with the interrupt sources in the PIC. So incon here binary 1001 here. You look at this register. 1001. INTE is related to RB0 external sources interrupt. GIE must be enabled because you are going to use interrupt. So no matter what, global interrupt must be on. So that's why you on another one here. Now this partner will be over here, INTF. The partner for the flag. By default, this value is 0. If there's no interrupt, the value will be 0. There will be no change. So now, move to that one. Count is equivalent to 0. Count is a variable. You declare it as an unsigned. So it starts from 0, 1, 2, 3, 4. You're going to add up that number. Now, you go to the while one loop. So this is a continuous loop. So go in here. Port C now is automatically as count. Count is equivalent to 0, correct? So by default, by initial program, your port C will all turn off because the value count is equivalent to 0. That's why when you run your program, your 7 segment just now over here starts with 0. This one starts with 0 because your port C now is count as 0. Betul tak? So now is all your port C now is all 0. This is number 0 because it's a number 0. So when you hit the button, that is not a switch. When you hit the button, you are telling the PIC to do the interrupt function. You push the button, it will go to do the interrupt. The interrupt function is like this. Once you push the button, the interrupt will go here. Now you will check if incon.intf, this command is to check this particular bit in the register. If any interrupt happen, this will be flagged to 1. So this is equivalent like if incon.intf is equivalent to 1. Is like that. It's checking whether the flag is 1 or 0. So if the flag is 1, then you have to count plus plus. So right now the count just now is 0. Plus plus means plus 1. So now your count is 1. The next command is very important. This command is incon.intf is equivalent to 0. This is very important command to clear back the flag over here. Just now your intf is equal to 1. This command is to reset back the value. If you do not reset the value, the system will think that it always have the interrupt continuously. You can run after this, So after this one have been declared, have been cleared up, so the last command is port C is equal to count, which is number 1 just now. Go back here. Now your port C is equal to 1. That's why your 7 segment now changed to 1. Waiting for the next interrupt. You push that the button, it will go up again and do the same function again. Up to how many times you push the interrupt. So now try to remove this command out. You can remove this command out. Look at the results. What it will be the results on the 7 segment display. You remove this command. Because I want to tell you that this command is very important. If you have the interrupt functioning. You remove this one, you can just comment out and you compile again your program and run it on your Proteus. You can remove that command line. put delay, you can put delay. You can put delay ms over here. After count, you can put delay underscore ms 1000. Look at the result again. Put the delay ms. Look at the result. The delay is for you to look because you cannot cache the computer. So you just want to see the result. Just put the delay over there. Just now you input this one, right? You change it to delay underscore s. You can see the result is still actually delay interrupt. Because you do not have this command, the system thinks that the flag is always 1. It's saying that it's always got interrupt. So it has to go to the interrupt functions to execute. So this is very important on this command. This command is to clear back the flag bit of the interrupt for RB0. Can you see it or not? Alright, so put back over there. Put back over there. So the command, you need to have it. You need to clear back the bit for the flag. Must put back. Then you can see that the interrupt does not happen continuously. It will wait for the input for RB0 and then the interrupt will do again. Okay, understand? Alright, now. Here is the component. You must remember that all the interrupt have its partner lah. So now TOIE, INTE is partner with INTF. This is the flag. So this is the first one for RB0 interrupt. So let's go for the second one. RB4, RB5, RB6, RB7 change interrupt. This is the second one. So write down this program faster. Look at the results again. Use the same Proteus design. We want to show you guys what is the difference on the interrupt versus switch today. Must confirm, So you have to write down. That's why in my class, every time you write down a command,